Hello, and continuing on with Physics 2, we're on section 3.5. So we've learned how to calculate electric fields. Now we're going to look at the superposition principle, which is going to be one of the base concepts for this semester. So the superposition principle is the net electric field due to two or more charges is the vector sum of each field due to an individual charge. So in other words, if you want to know the total electric field at a particular location, you need to find all of the charged objects in that region, calculate all of their individual fields, and then add them together. So superposition holds for other fields as well. So for example, gravity. If you wanted to look at the gravitational force on an object, so let's say you've got a star here, and then you have a black hole over here, and another star over here, the gravitational force on this object would be the vector sum of all of these massive objects in the area. All right, so as I said before, the superposition principle is going to be one of the key concepts that we cover in Physics 2. And a couple of things that we need to know about it. So when you're looking at the force on a field, so the force on a particle comes from the net field. It's related to the particle's location. So if our particle is here, it will be related to the location within this field, and it won't experience any self-force, so no self-force. And the fields do not get used up. So in other words, this particle here will have the same impact on A, regardless of whether or not there's other particles in the area. But if you're looking for the net field, then you'll need to sum them all together. All right, and this will become apparent as we go through. And another thing to note is fields go through matter, or electric fields go through matter. Okay, so let's do an example with the superposition principle. And one thing that's going to be really important as we're doing the superposition principle is to make sure that we're keeping track where is our observation point from, and then what is bringing all of the field to the observation point. And if you move your observation point, your field is probably going to change. So remember, when we were looking at the fields around point particles, they got weaker the further you were away from them. Okay, so let's look at an example. So we have the electric field and force due to two charges. So a small object with charge Q1 is equal to minus 3.2 nanocoulombs is at 0, 0, 0 meters. Q2 is equal to 7.4 nanocoulombs and is at 0.02, 0.09, minus 0.01 meters, what is E net at location A, which is at minus 0.06, 0.09, and 0.03 meters. And this will, of course, be due to Q1 and Q2. These are the two charged objects that are bringing the field that we're going to be summing together. Now, after we calculate the field, the next thing we want to know is what is the force on Q3, which has a charge of 8 nanocoulombs, if it was placed at location A. All right, so when we're reading a problem like this, it's really important we keep track of everything. So in this case, location A is our observation location. And then our sources are coming from the origin and this place here. So even though one of the charges is at the origin, we're not actually observing from the origin. We are observing from minus 0.6, 0.9, and 0.03. Okay, so when you've got a problem like this, you really want to go ahead and make a drawing of what's going on, and you can use this drawing to give you an idea of what your final answer is going to be. Okay, so if we're at location A, we want to draw our two charges Q1 and Q2. So if we look at where location A is, so it's with respect to Q1, Q1 is at the origin, so this is over to the left and up. So Q1 is here, and then if we look at where Q2 is, it's with respect to A, it's on the same place in the y-axis, so we can say Q2 is about here. Now we know Q1 is negative and Q2 is positive, so now we want to think about what the fields are from each of these. So let's go ahead and do Q1 orange. So Q1 is negative, and we know that when you've got a field from a negatively charged object, it's going to point towards the object. So the electric field caused by charge 1 is pointing towards charge 1, and the electric field caused by charge 2 is going to point away from charge 2. Now I've not scaled these two fields in this drawing. I'm just going for the general direction of where's our net field going. So if we were to add these two together, we would see the E net would be in this direction. So we can see that it's going to be in negative y and negative x. Now this is just a two-dimensional drawing, so I'm not have not drawn in the z-axis, but you could do a similar setup to find out where it is in z using a drawing before you even start to make a calculation. This is super useful for checking to make sure that you've not lost any negative signs. Also, if I see that you've drawn a correct picture and something else has gone wrong in your problem, this at least lets me know that you have the right idea. All right, so we want to calculate the electric field. So we know that that's going to be equal to 1 over 4 pi epsilon naught Q over r squared times r hat. So we know Q, we know our constant. We are going to need to find these values, these two values here. So we're going to need our r vector so we can find r magnitude and r hat. So let's start by Q1. So we're going to find the electric field for charge 1 and charge 2 and sum them together to get the net field. So R1 is going to be equal to the observation location minus the source. So R1 is equal to minus 0.06, 0.09, 0.03 meters, minus 0, 0, 0. My favorite type of math problem. So R1 is equal to minus 0.06, 0.09, 0.03 meters. We can go ahead and take the magnitude of R1. So this is going to be the square root of the components squared, minus 0.06 quantity squared plus 0.09 quantity squared plus 0.03 quantity squared. R1 magnitude is equal to 0.112 meters. R1 hat is going to be the vector R1 divided by the magnitude of R1. So this is equal to minus 0.06, 0.09, 0.03 meters divided by 0.112 meters. R1 hat is equal to minus 0.536, 0.804, and 0.268 meters. No meters. All right, so the electric field due to charge 1 at location A is going to be 1 over 4 pi epsilon naught Q1 over R1 squared times R hat. This is equal to 9 times 10 to the 9 Newton meter squared over Coulomb squared times minus 3.2 times 10 to the minus 9 coulombs over 0.112 meters squared times our R hat, so that's minus 0.536, 0.804, 0.268. And so E1 is equal to 1,230 minus 1,845 and minus 615 newtons per coulomb. Okay, so now we have the electric field due to charge 1. We need to find the electric field due to charge 2, and then we're going to add these two things together. So R2 is equal, so to do that, we need to find R2. Once again, we need the observation minus the source. And the observation stays the same, so minus 0.06, 0.09, 0.03 meters minus 0.02, 0.09, minus 0.01 meters. So our R2 vector is equal to minus 0.08, 0.04 meters. Then we can just find the magnitude. So minus 0.08 quantity squared plus 0.04 quantity squared is equal to 0.089 meters. R hat, the R2 vector divided by the magnitude, and this is simply minus 0.899, 0.449. All right, so the electric field due to charge 2 is equal to 1 over 4 pi epsilon naught Q2 over R vector 2 quantity squared times R2 hat is equal to 9 times 10 to the 9 Newton meters squared over Coulomb squared times 7.4 times 10 to the minus 9 coulombs divided by 0.089 quantity squared times minus 0.899, 0.449. And that gets us the electric field due to charge 2 is equal to minus 7,558, 3,775 newtons per coulomb. Okay, so now we need our net field, E net. Our net field is equal to E1 plus E2, which is equal to 1,230 minus 1,845 minus 615 newtons per coulomb plus minus 7,558, 3,775 newtons per coulomb is equal to minus 6,328 minus 1,845, 3,160 newtons per coulomb. So all we did there is we knew the charge, we know the constant for the electric field equation. All we needed to do was find the correct distance vectors, and remembering that the distance vector is not relative to the origin being 0, 0, 0, but it's relative to the observation location. And then once we had that, we could just plug and chug along and then do a simple vector addition. All right, so to round this problem out, we want to find the force caused by this electric field on a charged particle. So if you recall, Q3 is equal to 8 nanocoulombs. And so the force on charge 3 is going to be equal to the charge Q3 times the net electric field. This is equal to 8 times 10 to the minus 9 coulombs times minus 6,328 minus 1,845 and 3,007. Oops, nope, that's not right. 3,160 newtons per coulomb, and the force is equal to minus 5.06 times 10 to the minus 5 minus 1.476 times 10 to the minus 5 and 3.02 times 10 to, oops, nope, 2.53 times 10 to the minus 5 newtons. And so there you go. All right, so I will record section 13.6 as a separate video.